Hello to everybody. Thanks for watching this presentation. It was prepared for ILP Task Force CoLiBrI, which means Continental Lithosphere Broadscale Investigation. My name is Roman Pašteka. I am a university professor at the Comenius University in Slovakia, and together with my colleagues we would like to present results from a very interesting reprocessing project, the compilation of the new pan-Alpine Bouguer anomaly map. As you may know, anomalous features of the Earth's gravity field belong to important tools for geologic and tectonics interpretation of the lithosphere. Today, there exist huge new datasets received from various satellite missions, but there is still a great potential in terrestrial gravity databases, which were observed on the Earth's surface, and therefore they contain much more details and are closer to the sources in the lithosphere. And such gravity databases exist in many countries, but there are problems in their use. At the first point, some restrictions because this data can be a property of various companies and institutions. And the second reason, in each country, the acquired gravity data were processed in a little different way, so it is not a simple task to bring them together. Based on an intensive communication from the side of Professor György Hetényi and Professor Hajo Götze with other experts from the area of gravimetry, a scientific network called AlpArray Gravity Research Group was created in year 2018 as a part of the main AlpArray scientific program. 10 countries from the pan-Alpine area, you can see them in the figure in the map, have contributed with their national gravity databases. New approaches to the calculation of Bouguer anomalies have been proposed and discussed, and finally all these terrestrial data were recomputed in a new pan-Alpine surface Bouguer anomaly map. My colleagues Dr. Juraj Papčo, Dr. Pavol Zahorec and Professor Miroslav Bielik will now present all the details of this amazing project. Juraj will speak mainly about the geodetic aspects of the data management. Pavol will explain you the improved way of the Bouguer anomaly computation together with terrain and bathymetric corrections computation. And finally, Miro will guide you through the tectonic features of the new pan-Alpine Bouguer anomaly map. So enjoy it.
Hello to everybody, my name is Juraj Papčo, I'm geodetist from Slovak University of Technology, and I will continue with the data preparation and homogenization. One of the key problems in the unification of gravimetric databases is the homogenization of position, height and gravimetric coordinate system used in each database. Through its historical development, each country has used and sometimes still use local system and then realization frames, which are often based on the established principle of reference system using older ellipsoids or older geodetic reference network and projections. These systems and their realization, practical realization, thus contain several differences which are responsible for large inhomogeneities, shifts, errors in the position, height and gravity. These errors are most evident in the mutual comparison of data from individual countries. To avoid these problems in the position or gravimetric points, all data were transformed from local national positioning reference system to the European terrestrial reference system 1988, which is very accurate, homogeneous and recommended for all European countries. Similar situation is also in the vertical direction. The countries use a different national height system, different ellipsoid, different type of heights, different quasi-geoid, And the solution is again to transformation from national height system, which consists of the geoid or quasi-geoid, to the ellipsoidal height using or based on ellipsoid GRS 80. The situation is similar in gravimetric reference system, in which especially the gravimetric databases that have been creating for decades often use old gravimetric system linked to the Potsdam gravity system, and it is very important step therefore to convert this old data into gravimetric system which are connected to the absolute gravimetric points or measurements like IGSN 71 or modern national system connected to the new absolute gravimetric measurements which are verified by international comparison of absolute gravimeters. To conclude introduction to the homogenization, we can see this slide where our summary of homogenization we can use for local position transformation, national authorities or national transformation services like SAPOS in Switzerland or ESCAPOS in Slovakia. We can use also transformation implemented into standard GIS tools or programs, or also we can use our own software implementation which is based on national standards, information and experience of individual responsible institution. We try to connect and control all this transformation with official EPSG database, which is organization or initiative for collecting all possible transformation for position, vertical system, to have very detailed information and parameters for transformation. In the elevation, for the practical transformation from physical heights based on geoid or quasi-geoid, we use available local geoid or quasi-geoid model. Also, we are using or we can use local transformation service, or we can use a global service for creating or preparing data from global geopotential model like Eigen 6C4, which is very accurate in the Europe. Another very important part are metadata, because we want to control each step of this transformation and homogenization. So it is very good to have metadata about the origin of the coordinate system, about the position, about the practical realization, about the creation of the geoid, about the coordinate system used for position for the gravity measurements, what was the adjustment on transformation between the Potsdam system, between the IGSN 71 system, and so on. All this information and recommendation and steps were consequently used within the AlpArray project. So we requested from individual country their gravimetric database. Each country provide basic data like position of the gravimetric point, height, and gravity value, if it is possible, for each gravimetric point, and also metadata. The metadata consists from information about the local coordinate system or national coordinate system, about the local geoid or local vertical system, the type of the height which is used or which was used within the gravimetric data, and also gravity. For data sets, in which we have all information. We perform independent transformation check. We control the transformation between local coordinate system and the global coordinate system ITRS 89. Also, we check the differences in position, and in majority these differences was less than 1 meter, which is very good for especially very old gravimetric data. All differences or large differences were individually investigated and then solved problem with local transformation or local information, local metadata. Similar situation was for the heights. We check the quality and differences between the ellipsoid height provided by individual country or institution, comparing our transformation using physical height and recently available model of geoid or quasi-geoid. These differences were generally less than 50 centimeter, and same situation like with problems with position. We check all larger differences, and in majority it was due to the problem with the precise or exact position of the gravimetric. After all of these preparatory and homogenization steps, we have in total available more than 1 million good gravimetric points. We can see the distribution, spatial distribution of the points. You can see that several countries have a very good spatial coverage, like Slovakia, parts in Austria, also in Germany, Switzerland, Po Basin in Italy, France. Also we can see that the mountains area are very pure with the distribution of the points. So this was very big challenge for us to prepare and to deal with this problem and use the other type of data, especially satellite data, to combine data with terrestrial information. Here you can see the table or list of the points and from each country what was the number of the points which was provided to the database. One of the very important elements in the complete Bouguer anomaly calculation process is the determination of mass correction. The key element for quality and reliable determination of mass correction is the use of reliable and accurate digital terrain model. We have to distinguish between digital surface model, which consists of points from bare earth, from buildings, from trees, from artificial objects like cars or poles, compared to digital terrain or relief model, which consists or which is created only from points from bare earth. Since our approach to mass correction computation are based on calculation in different zones, it is very important to provide suitable models with the appropriate resolution and quality. The nearest zone up to maximum 5 km is the most critical, and especially the nearest zone up to 250 meter is the most critical. Hence, for this zone, it is the best to use the high quality models based on LiDAR technology or digital photogrammetry with the highest possible resolution, like 1, 5 or 10, 25 meter. For outer zones more than 5 km, up to the 167 kilometer. We call middle zone. It is very suitable to use digital elevation model with medium resolution, 1 to 3 seconds, with which uniformly cover the whole territory, have the same shape, representation and accuracy, and can be converted with local geoid or quasi-geoid model to the ellipsoidal heights. For good and high quality complete Bouguer anomaly, it is necessary also include information from the seas and oceans or large lakes for computation of bathymetric correction. We use regional bathymetry model, which consists from local and from global and local. So for each country, we try to collect the best available local model based on LiDAR or digital photogrammetry data. Here we can see the models and acronyms of institution which provide this data for us. Each of these models was tested on a set of gravimetric points. Here we can see the table where we can see also the grid step of each model, the source of the model. Only for two countries, Croatia and Italy, we were not able to acquire a local model, so we use a global model, MERIT. As I mentioned before, each of these models was tested. We select points, gravimetric points located at least 500 meters from the border of each country. This test show us or we can detect possible artifacts in the dams, especially in the high mountains area, and also it was a primer filter of the quality of the position of the gravimetric points. Here we can see the histograms for each country and the statistical table. The best data were from Switzerland and Germany. Here we can see the spatial distribution of these errors or differences between measured value of the height, of the ellipsoidal height, and the interpolated value from each local model. Several points exceeding the threshold plus minus 50 meters of these differences, and these points were separately assessed and subsequently excluded from the database. For the calculation of mass correction within the middle zone, as I mentioned, it is very suitable to use the global digital elevation model thanks to the remote satellite techniques. Several commercial or freely available digital elevation models are currently available. We tested SRTM model, ASTER, ALOS, WorldDAM, MERIT, which is very good, and EUDAM. Each model was individually tested. Here we can see the differences between visual differences between the LiDAR model on the left side, the SRTM, which is one of the most used model in the world, and on the right side there is a MERIT model. The resolution here is about 10 meters. It is part of Austria. Here it is 1 second. It is approximately 30 meters, and here it is 3 seconds, approximately 100 meters. We can see the shape or artifacts here in SRTM model, and it is very plain near the river. It is very close. Also, we can see in the MERIT small discrepancies, but they are not so big like in SRTM. All models which were tested represent digital surface model. only the merit model has partially removed vegetation and represents a mix of the digital surface and digital terrain model. From these models, the best one is merit due to the removal of majority errors, components like absolute biases, stripes, speckle noise, and canopy height. This was confirmed also by independent comparison at selected gravimetric points with new, very precise measured point position with GNSS in Switzerland or Slovakia. You can see on the histogram that the majority of the large errors are due to the canopy. The merit model was used also in original 3 arc-second resolution, and for the two countries, Croatia and Italy, was also used for the T2 zone calculation, and here the original resolution was resampled to the 25 meter resolution. Here you can see the overall quality test of the merit model. Here you can see the differences. The largest differences are logically in the mountains or here in Italy. These differences are mainly caused by the wrong position of the gravimetric points. The last part of my presentation will be about the bathymetry model, which we use for bathymetric correction. We select IMODNet DTM model with 3.75 second grid, which is very new and very good quality. This model comes from JEPCO grid data with local coastal measurements. Here you can see the portal. It is open and free available, and it is very good model for this kind of calculation with very good resolution and quality. Here you can see the graphical interpretation of the depth of the sea. Some parts are very good, have a very good coverage with the local measurements, especially in the coastal area. Some parts are not so good. This data, it will be a big challenge for next decades to cover these gaps with very good and appropriate local or satellite measurement. Last but not least, part of the bathymetric correction deals with the effect of the lakes. We have information from bathymetry, from the measurements or topomaps, from old topomaps for Austria, Germany and Switzerland. In Germany and Switzerland we have information in the grid with 25 meter resolution. From the Austria we have information with the grid within the grid more than 300 meter. Here you can see the image of the depth of the two largest lake, Geneva lakes and Bodensee, between Austria, Switzerland and Germany. So many thanks for your attention. This was everything from my part about the data preparation and homogenization. If you have any question, please don't hesitate to contact me and ask what is not so clear. And if you have any question, please contact me.
Hello everybody, my name is Pavol Zahorec. I'm from Slovak Academy of Sciences. During the project I was responsible for calculating particular steps. It means mass correction, bathymetric correction, lake corrections, and finally the computation of the Bouguer map. In the next short presentation I will describe these particular calculations. So the basic formula for Bouguer anomaly calculation is here. It is taken from Moyers et al. 2001. Normal field is calculated with parameters of GRS80 ellipsoid. What is important to say is that we use the concept of ellipsoidal heights. It means that the calculated anomaly implicitly includes what we call geophysical indirect effect. As you may notice, in the case of bathymetric and atmospheric correction, we use normal heights. So I will show you why on next slides. From my point of view, the most important was the calculation of mass correction and bathymetric corrections because these corrections had to be unified for all countries. In this picture, I will try to show the meaning of these corrections, especially for the concept of ellipsoidal heights. In the top picture, we have the classic concept of physical or normal heights. It means from sea level. Mass correction represents topomasses above sea level. In the bottom picture, we have a situation with ellipsoidal heights. In the situation in which we are in the AlpArray area, the ellipsoid is below the level of the geoid. It means that in the case of mass correction, we have additional topomasses that we can easily calculate. But we have a more complicated situation on the oceans because we have quasi two kinds of water masses here. Masses below the ellipsoid level are equivalent to masses in the classical concept of normal heights, but water masses above the ellipsoid level must be considered differently. Since these masses are above the reference level, we must treat them as topomasses. It means we have to calculate them with the real density 1.03 instead of 1.64. Fortunately, we can make the calculation easier. We don't have to separate these masses and calculate them separately, but we can get the effect for density 1.03 as the difference of two effects. One for density 2.67 as part of topomasses, mass correction, and the second for the density 1.64, which is as a part of bathymetric corrections. It means that we calculate just two corrections, mass corrections for 2.67, including water layer in ellipsoidal heights, and bathymetric correction for 1.64 in physical heights. This picture is just to show the real situation with real elevation models, comparing two models on land and at sea, just to see that it is the same situation as the previous model situation. Now I will say something more about calculating mass corrections. First, here is a picture that clearly shows the difference between what we call mass corrections or near topographic effect and what we often call terrain corrections. At the beginning of the project, it was important to choose a good, suitable software for calculating corrections. We choose from two software developed within research group. The comparison show some advantages of the TopoSK program, and so we use this program. A few words about the basic characteristics of this TopoSK. The calculation is made in 4 zones according to the table. The very important is the inner zone, where a detailed calculation using a polyhedron and a highly detailed digitalization model is used. As the most important attributes of our program, we can mention exact calculation of the topographic effect or mass correction in the arbitrary point location with regard to the real topographic surface. It means above or below the surface. Then detailed approximation of the inner topography by 3D polyhedral body. Very detailed topographic models are applicable. There is optional concept for interpolated heights of calculating points within the net zone, and there are alternative computing methods, interpolation methods, and so on. On this map are displayed calculated mass correction values calculated up to distance 166.7 km and for density 2.67. You can see that they reach really significant values, almost 400 milligal. The picture in the lower right corner shows their height dependence, and for comparison also the effect of a spherical layer with a constant thickness. It is the red line. The difference between these two values represents what we call terrain corrections, and they reach almost 100 milligal. It is also interesting to see that the mass corrections also reach small negative values, these dark blue points, which is logical in the case of points in deep valleys or near the coast, where the topographical masses around these points are situated above their level. This next map shows bathymetric corrections for density 1.64. Only non-zero values are displayed on this map, so the rest of the land area is not displayed here. It can be seen that offshore this correction also reach significant values, important mainly for marine data. The comparison with the frequently used planar approximation in the upper right corner of the figure, unlike mass correction, these differences are not systematic and they reach about 30 milligauss. Because the elevation model used in the mass correction calculation usually include the volumes of the water masses of alpine lakes, Great Lakes, these volumes are calculated with in incorrect density. It means 2.67 instead of the real density 1 for water. So we can eliminate this by the application of lake correction. This picture just shows an example of the lakes model for the used for the calculation in the case of the Switzerland. The way how we made the calculation is shown in the following picture. We incorporated the lakes model into the existing elevation models, and we made the calculation of the mass correction twice. It means the difference between these two calculations defines the lake correction using density of 1.67. Which is the difference between the density of topomasses and water. This picture shows the values of lake correction. They reach maximum values of about 5 milligauss, especially on the lake sides with steep mountain flanks. Again, it is interesting to see small negative values which are in the deep valleys with topography below the level of the surrounding lakes. So now a few words about completing the Bouguer map from other sources where we didn't have available data. For the peripheral areas of the maps, which are marked by red, we decided to use GGM, Global Geopotential Model data. Before that, I would like to remind that for the southeastern part of the map, which represents the area of the former Yugoslavia, we also had another source. It was the original Bouguer map of former Yugoslavia. We converted this map to digital form, and then we recalculated the Bouguer anomaly into form which is compatible with the project. Comparison of such transformed original map on the territory of Croatia showed general agreement without systematic errors. So therefore, this map was used for the area of Serbia and Bosnia and Herzegovina. For the rest of the map, as I mentioned, we use the GGM data. Specifically, after some testing, we choose eigen model. Whether it is a good idea or not, we test it in the main area where we have available data. The upper left picture is a Bouguer map from terrestrial data. The right is a map from eigen data. Qualitative agreement is visible, of course. The quantitative differences between these two maps are at the maximum of the tens of milligauss. Mean error is about 4 milligauss, but what is important is that there is no systematic error. This is the result, complete Bouguer anomaly map. In the next part of the presentation, our colleague Miroslav Bielik will continue with its description. If you ask what is the accuracy of this map, the answer is not easy because the heterogeneity of the sources. In the case of countries with good terrestrial data coverage, such as, for example, Slovakia, a test on independent gravity points, it means points that were not included in the map compilation. This test showed an error with standard deviation less than 1 milligauss, maximum differences of about 5 milligauss. Of course, such a situation is not valid in general, and of course, we do not have the possibility of such detailed testing. One possibility how to roughly test the global accuracy of data is a cross-validation process. The result of this process is in this picture. You can see the differences are larger, of course, up to about 20 milligauss maximum, but the standard deviation is low, is less than 1 milligauss. At the end of my presentation, I would like to mention that we also focus marginally on other calculations that may bring an improvement of Bouguer map in the future. So one of them is the calculation of atmospheric correction using so-called true atmosphere. It means it is the model of atmosphere with radially dependent density and with the bottom surface defined by the Earth surface. And the calculation is made globally. And the second effect, much larger, of course, is the distant relief effect. It represents the combined effect of the topography and bathymetry beyond the standard distance of 166.7 kilometers, also calculated around the whole Earth. Consideration of this, of course, time-consuming calculations is for future studies.
Now, we would like to present you a short overview of the features of the new pan-Alpine Bouguer anomaly map. From time limit, we will focus our attention only on the most dominant gravity anomalies. A complete descriptions of Bouguer's anomalies can be found in our article, which was published this year in journal Earth System Science Data. The most dominant feature of the complete Bouguer anomaly map are two regional anomalies. The first one is represented by high negative, more than -100 milligauss, while the second anomaly by high positive, more than +150 milligauss of gravity values. The most dominant regional gravity anomaly consists of the northern and southern parts. The northern parts is represented by Alpine gravity law, which is characterized by the gravity values ranging from -100 to -170 milligauss. The Alpine gravity law coincides very well with the Alpine high topographic change. It could be divided into 3 local gravity laws that correlate with the Western Alps, Central Alps, and Eastern Alps. The southern parts is represented by the Po Basin gravity law. The gravity values here range from about -80 to -140 milligauss. This gravity law continues in southeast direction to the central Apennine gravity law, whose amplitude -40 milligauss is significantly smaller in comparison with the Po Basin gravity law. A significant anomaly features represented by a very narrow local gravity high can be clearly recognized between the Western Alps and the western parts of Po Basin gravity law. This anomaly is well known as the Ivrea gravity high. It is characterized by maximum values of +40 milligauss, but it is important to note that its relative amplitude against the gravity laws in the Western Alps and the Po Basin gravity law reaches up to 160 milligauss, and from this point of view, both sides of the Ivrea gravity high are represented by the highest horizontal gravity gradient in the study region. The second dominant regional gravity anomaly is represented by the Mediterranean gravity high. This anomaly consists of 2 gravity highs, the Corso-Ligurian gravity high and the Tyrrhenian gravity high. The Corso-Ligurian gravity high, the values is characterized by the maximum values +200 milligauss, while in the Tyrrhenian gravity high, the values don't exceed +140 milligauss. Both gravity highs are separated by so-called relative Corsica-Sardinia gravity law. The Adriatic Sea is largely characterized by the positive gravity field in which the South Adriatic gravity high dominates. Here we can monitor the values in interval from approximately +20 to +100 milligauss. Its maximum is located over the Gargano promontory. In the western parts of the Istrian Peninsula, we can see the residual Istria gravity high with maximum values of +30 milligauss. In the Eastern Alps, the Alpine gravity law splits towards the east in 2 branches of less pronounced gravity laws, the Western Carpathian gravity law and Dinaric gravity law. In the Western Carpathians, values vary in interval from 0 up to -60 milligauss, while Dinaric values range from 0 up to -120 milligauss. The lower amplitudes of both gravity laws in comparison with Alpine gravity law most likely reflects a weaker continental collision resulting in funiculars under the Carpathians and Dinarites. The Pannonian Basin, located between the Western Carpathian and Dinarites, is accompanied by a relative regional gravity high whose values range in practically very narrow interval from -10 to +20 milligauss and includes several local positive and negative anomalies. The gravity over the Apuseni mountain is negative with maximum values of -80 milligauss. The rest of study area, which is located in the western and northwestern parts of this map, is accompanied by variable gravity field with the values varying generally from -80 to +40 milligal. We can recognize here the following anomalies: the Pyrenean gravity low, the Massive Central gravity low, the Paris Basin gravity low, the Rhône-Breze-Graben gravity high, the Apennine Graben gravity low, the Black Forest gravity high, and Vosgian gravity high. The further anomalies region is formed by the Bohemian Massive, which can be divided into several subparallel positive and negative belts with predominantly northeast-southwest orientation. The gravity of the Franconian platform area ranges from -40 to +15 milligal. The Rhenish Massive is asymmetric, positive over the eastern and positive over the western parts. The Ardennes are accompanied by the gravity low of -20 milligal, and finally Brabant Massive is manifested by a gravity high with amplitude +20 milligal. So, dear listener, so this is briefly all about descriptions of the most dominant and the most interesting total Bouguer anomalies. Thank you for your attention.
In the end of this presentation, we would like to acknowledge to the whole AlpArray Gravity Research Group for the support of this admirable project. For additional information, we recommend our common publication in the journal Earth System Science Data.